Good morning, gang. So today is our review day for exam 2. You can talk about whatever you guys would like to talk about. We can do some curve sketching. We can do some problems from the study guide, problems from the homework. It is 100% up to y'all. So just like our review for exam 1, I'll ask you to open up your chat dialogues and type in there what you would like to see, what you would like to work on today. We can get straight to it. You may have noticed, I'll turn on my screen share, that I uploaded a video with the correction. What was it? To the link from the 20th. So the video for the lecture, and then there's that mistake on the last problem at the end, and then I made another video to correct that mistake. So you can see that there if you want to. But for now, I would like for us to get into our review materials. So what would you guys like to do for our review today? Number 10 from the study guide. Can definitely do that. 3 and 5 from the study guide. And number 15. Okay, so let me address some of these study guide problems. Number 2 is actually an old homework problem, right? So this very problem was in the homework, and I'll do, we've got 3 parts here. So I'll do one of them. U is f of g, v is g of f, w is g of g. I'll do part A. This is the second study guide, the second question. I'm going to leave the graph up here. And the dot can come here. This can close. This can come back up. Okay, so you should be able to see my writing in the background there. We're going to go ahead and do number 2 from study guide 2. So that's SG2 number 2 in the corner there. We're told that U is f of g of x. And we're given the graphs of f and the graphs of g. And we're asked in part A to find U primed of 1. So U primed of 1 is the derivative of U evaluated at x equals 1. So I need to find a formula for the derivative of U as best as I can. And then I'm going to plug 1 in. Since U of x is f of g of x, U primed of x, this is a chain rule thing. You differentiate the outer function, leaving the inner function alone. So it's f primed of g of x. And then you multiply by the derivative of the inner function. So we're multiplying by g primed of x. This means that U primed of 1 is f primed of g of 1 times g primed of 1 So I'm just putting 1 everywhere there was an x in my formula. So I needed this formula, which came right from the chain rule, and then I plug in 1. And now I look to my graph. I need g of 1 and g primed of 1. So I look along my x-axis, which is here. You can tell what the x-axis is because it's got the arrow and the x there. And I come over here 0 to 1. All right, so g of 1 is 1, 2, 3. So this is f primed of 3. Is the inside there, g of 1 is 3. That's from the graph. And g primed of 1 is the slope of g at this point. Now what's the slope here? It's a little bit tough to tell, but I go through this point, and I go through this point, and this whole segment here is a straight line, so the derivative is constant there. So what is that slope? Well, I go over 1 and I go down 1, 2, 3. So the rise over the run there is -3. This is because g of 1 is 3 and g primed of 1 is -3, both coming from the graph. And now the last thing I need to do is figure out f primed of 3, which I also get from the graph. So I look on the red graph, the graph of f. I come out here to x equals 1, 2, 3, and I need to sort out the slope here. So the slope here is the same as the slope anywhere else in this portion of f, because f is piecewise linear. It's a straight line there. So I come out 1, 2, 3, I look up here, what's the slope here? Okay, well the slope here, I look at the rise over the run for this piece. So I go down 1 and over 1, 2, 3, 4. So it looks there like the slope of f everywhere in this region is -1/4. So this is -1/4 times -3, which is +3/4. Parts B and C go the same way. And again, because this is an old homework problem, I really don't want to, study guides are meant for you to work on. I don't want to grind you up here and do all of this. So this is how you do part A. Parts B and C go the exact same way. You start with the formula, right, which they give you, like u of x equals f of g of x, or u of x, or v of x equals g of f of x. You differentiate using the chain rule, and then you plug in. After you get to this step, you need to look back at the graphs to figure out all the little pieces. Okay. So we also wanted to see 3 and 5 from the study guide, 3, 5, and 10. 3 asks us to differentiate g of u equals the natural log of the square root of 8u plus 3 over 8u minus 3. And you could jump in here and start going crazy with the chain rule and the quotient rule, but you really shouldn't. The purpose of this problem is to remind you that you should do as much algebra as you can to simplify before you start differentiating. If you jumped in right here, you're going to need a chain rule to get through the natural log stuff. You're going to need a chain rule to get through the square root stuff. And then you're going to need a quotient rule for the inner derivative. And remember, each time there, you've got your chain rule is a little bit complicated. You're not just differentiating. You're like differentiating the outside, leaving the inside alone, multiplying by the derivative of the inside. So it would really stack up in a nasty, nasty way. You don't want to do that. Think of this like the logarithmic differentiation problems that we were doing back in section 4.2, I think. You're going to expand this log first. So this is 8u plus 3 over 8u minus 3, all to the 1/2 power inside my logarithm. That's where we begin. Rewrite the square root as a 1/2 power. And then you'll recognize that this 1/2 power can come down in front of the logarithm. So I'll continue it as far over here as I can to conserve as much space. This guy is the same as 1/2 times the natural log of 8u plus 3 over 8u minus 3. And it's already looking better. I've already gotten rid of one of the chain rule steps I would have to do if I was going to jump in and differentiate, because now no more square root. That square root inside is the same as a 1/2 multiple outside. The last thing I'm going to do before I differentiate is use the other rule for logarithms that discusses what I do if I have division inside of a log. Division inside of a log, remember, is the same as subtraction outside of the log. Everything was underneath that square root. Everything had the 1/2 power. So the 1/2 power is going to need to go to everybody. In other words, I'm going to use some parentheses or brackets when I do this. I'll have ln of 8u plus 3 u minus ln of 8u minus 3, and then close that bracket. I can distribute my 1/2. So I get 1/2 ln 8u plus 3 minus 1/2 ln 8u minus 3. And this is exactly why, way back in your algebra classes, we made you guys expand and contract logarithm statements so that you could do this sort of stuff. So far, I've done 0 calculus. All right. On this problem, I've done no calculus whatsoever. I've just done algebra to simplify, expand this log statement into this log statement. These guys are equal to each other, so now I can differentiate. And if I differentiate here, life is easy. I do still need the chain rule, but each little chain rule here is much, much simpler than it would have been if I jumped in right away. The 1/2 is going to come along for the ride. The derivative of the ln of 8u plus 3 is 1 over 8u plus 3 times the derivative of 8u plus 3, which is just 8. And then I've got this minus is this minus. The derivative of, so 1/2 will come along for the ride. And the derivative of the ln of 8u minus 3 is 1 over 8u minus 3 times the derivative of 8u minus 3 is 8. So remember, to differentiate a natural log statement, always you have 1 over the inside times the derivative of the inside. Now the 1/2s and the 8s talk to each other because everybody here is being multiplied. I can finish this by writing this as 1/2 times 8 times that, which is the same as 4 over 8u plus 3 minus 4 over 8u minus 3. And that's as nice as this is going to get. You could put these back together with a common denominator if you wanted to. I wouldn't require you to do so. This would be totally fine on a test. In fact, the line above I would accept on a test also. All right, unless you intend to go and do something with this derivative, there's no reason to simplify it any further than this. Questions on either of these first two? Okay, so study guide 5 is next. That one asks us to find critical numbers. Okay. So you have to remember what a critical number is. They're in the domain of the original. And either make h prime of t equal to 0 or h prime of t undefined. So your first thought here should be, what's the domain of the original? The original function here is t to the 3/4 minus 6t to the 1/4. And the 4 downstairs here, remember, is a fourth root. So the domain of the original h of t, which I can write as the fourth root of t cubed minus 6 times the fourth root of t, is the left closed right open interval 0 to infinity. I can't plug in negative numbers because of the fourth root here. All right, that's the idea. This guy gets upset if you try to plug in a negative value for t because he is an even root. When you plug negative numbers into even roots, you get non-real complex numbers out. So his domain is everything except for negative numbers, i.e. the left closed right open interval 0 to infinity. So next I calculate h primed, and I find anything that makes this guy 0 or undefined. I check whether or not those numbers are in here. If they are, then those are critical numbers. So h primed of t. This is just a power rule thing. The derivative of t to the 3/4 is 3/4 t to the negative 1/4. Subtract 1 from the power, bring the power down. And then I've got minus 6 times 1/4 t to the negative 3/4. And it's convenient that we're looking at this because this will allow me to share with you a nice trick. If you watched my correction video from, from Monday's lecture, then you've already seen this trick. But derivatives that look like this are fairly common. Derivatives where you've got like negative powers of some term here. Because that's what you get when you differentiate power rule stuff and these powers start out smaller than 1. There's a fast way to clean these up. The fastest way to clean this up, much faster than rewriting this as 1 over t to the 1/4 and 1 over t to the 3/4 and trying to have a common denominator, a hell of a lot faster, is to force factor the largest negative powered term out. So before I do that, 6 times 1/4 is 3/2. So this is 3/4 t to the negative 1/4 minus 3/2 t to the negative 3/4. I can factor out a 3/2. But let me first deal with the powers of t here to show you this cool trick. So I've got t to the negative 1/4 and t to the negative 3/4. Both of those have negative powers. If I want to clean this up as much as I can, the fastest way to do that is to identify which of the negative powers is larger. Here the negative 3/4 is definitely larger than negative 1/4. So I'm going to factor this whole piece out. I'm going to factor t to the negative 3/4 out. And I ask, okay, when I do that, what's left over? I'm going to ignore this piece just for a moment and say, okay, well, this piece, when I factor t to the negative 3/4 out, I'll just have 3/2 left. So I'll have minus 3/2 left from that piece. And then the question is, well, what about here? And remember, factoring is the same as like dividing out by. I'm dividing out by t to the negative 3/4. So this is going to be t to the negative 1/4 divided by t to the negative 3/4, which is the same as t to the negative 1/4 minus negative 3/4. And he had his 3/4 coefficient sitting there. So sorting out this power is the only tricky part of this, and it goes very fast. You just subtract the powers because you're just dividing out by this power, or you're dividing out by this term, so you subtract this power. So you'll see this will go a hell of a lot faster than the common denominator stuff. I get t to the negative 3/4 times 3/4 t to the negative 1/4 minus negative 3/4 is negative 1/4 plus 3/4. So negative 1 plus 3 is positive 2. So that's t to the 2/4. Is that right? Negative 1 plus 3, yeah. And then we've got our minus 3/2 here. That's 3/4. 3/4 minus 1/4. Yeah. Yep. 1/2. Okay, that works. So I get t to the negative 3/4 times 3/4. 2/4 is the same as 1/2, so this is the square root of t minus 3/2. And then I can set each factor equal to 0 on its own. Usually this power is going to come out to 1. Most of the time that power will come out to an integer, so I'm a little bit suspect here. 3/4 minus 1, I want to make sure I didn't make a mistake. 3/4 minus 4/4, it's good. That is negative 1/4. Yeah, no, okay, we're okay. No, it's just a relationship between these two powers. It didn't come out that nice this time, but it still comes out a hell of a lot nicer than it would have otherwise. I could play around with these constants a little bit. I can factor a 3. So I'll have 3t to the negative 1/4 times 1/4 square root of t minus 1/2. I could force factor out a 1/2 if I wanted to, but from here I'll just set each of these equal to 0. So I've got 1/4 square root of t minus 1/2 over t to the 1/4 and a 3 out front. And the question is, can I find the critical numbers? Can I find the places where the fraction is equal to 0? That will come from where the top is 0. Can I find places where the fraction is undefined? That will come from places where the bottom is 0. If I set the top to 0, and I'll say it like this, h prime, the whole derivative will be equal to 0 if the top is equal to 0, which means 1/4 square root of t minus 1/2 equals 0. So I'll add 1/2 to both sides, and I get 1/4 square root of t equals 1/2. Multiply both sides by 4, and I get square root of t equals 4 over 2 is 2. So t would be the square root of 2 or negative square root of 2. Oh, no, that's t squared, sorry. Just t equals 4. Sorry, square both sides. Yeah, just the one, t equals 4. It's because it's square root of t equals 2, not t squared equals 2. And then h primed is undefined. If t to the 1/4 equals 0, and if you raise both sides to the 4th power here, you'll find that that has t equals 0. So your critical numbers, t equals 0 and t equals 4. The last thing we have to check is that these are both in the domain of the original, and they are. All right, both of these are in the domain of the original function, so we're happy. So these are our critical numbers here. This trick of factoring out the largest negative power is a really nice trick. And you can do this in any expression like this. And the result here will always be nicer than what you started with, and it will always go faster than trying to have a common denominator. Okay. Any questions on the calculations here?
Yeah, how'd you go? What line is that? 1, 2, 3. The fourth line where it's t negative 3/4. How'd you get 3t minus 1/4 again? With the bracket 1/4 square root t?
So we're looking here.
Yeah.
3t. Oh, this should be a 3, shouldn't it? Yeah, did I copy this 3/4 as a 1/4? I think it should be. Yeah, you're right. You're right. Sorry.
That's okay.
So this term right here should be this term right here, and I just copied it down wrong. It's not going to actually have any effect. So that means that this guy is a t to the 3/4 downstairs. Yeah, good catch. Thank you. Which means that when we set the bottom to 0, we get t to the 3/4 equals 0. But then that has the same solution. That's still just 0 if t is equal to 0. Yeah, good eye. Thank you.
Excuse me, sir.
Yes.
Good morning.
Good morning.
To find a critical number, I think we take only the top equal to 0. So I don't know why you take on the bottom you take t 3/4 equal to 0. So can you explain to me?
So I'm looking for two different things here. Remember, critical numbers are places where h primed is equal to 0 or where h primed is undefined. So over here, I'm finding places where h primed is equal to 0. And that will happen if the top is 0, right? Because a fraction is 0 if its numerator is 0. So if I want to find where this whole apparatus is equal to 0, I just set its top equal to 0. But I also need to find anywhere that h primed is undefined. And that's going to be places where the bottom is 0. So I should say maybe here, if I want to do this similarly, h primed of t is undefined if the bottom equals 0, which means that t to the 3/4 would be 0. So if the top is 0, what you're finding there are horizontal tangent lines. If the bottom is 0, what you're finding are vertical tangent lines. And both are...
So for any polynomial function, we can proceed like that?
If you had a polynomial function, there would be no downstairs. There would be no bottom. So you would just set the whole thing equal to 0. But if your derivative...
Yeah, excuse me, it's not a rational function.
Yes, for any rational function, or any function whose derivative is a rational function, or even more generally, right? This isn't actually a rational function because the top and bottom aren't polynomials. Any function whose derivative is a fraction, you will set both the top and bottom equal to 0 to find critical numbers.
Okay, thank you.
Of course. Other questions here?
When we do the h primed of t is undefined and we have the t raised to 3/4 equals 0, what is the algebra that goes on there like to undo that exponent?
Fair question. So what I'm doing there is I'm saying t to the 3/4 equals 0. And then I'm, just like if this was t to the 1/2 equals 0, I would raise both sides to the power 2 to undo the power of 1/2. Here, I'm going to raise both sides to the power of 4/3.
Okay, perfect. That makes sense now.
Yeah, and then this will be t to the 3/4 times 4/3. That's our rules for exponents. Equals 0 to the 4/3, which is 0. And then when you multiply these, the 3's cancel, the 4's cancel, and you just get t to the 1 equals 0. But yeah, that's the procedure. You don't need to necessarily show this work for these. I'm assuming that you guys are comfortable with this algebra. If you have any power of t equals 0, the only solution there is going to be t equals 0. That's generally true. What else are we wondering? Anything else feel reasonable?
Yeah, so about the t equal to 0, so we can use that number to find the local maximum or local minimum.
Both of these would be used to find local maxes or local mins,
Local
potentially.
minimum.
Yeah.
Okay.
These are both critical numbers, which aren't always going to be a local min or a local max, but could be a local min or a local max. So this
Okay.
tangent line, this could look like a cusp. We could have something going on here like this, which would be a local min. We could have something going on there. Let's see if I can draw this like this, which would be a local max. Or we could have something going on there like, let's see, like this, which would be neither. So the derivative being undefined means that you've got a vertical tangent line at that point, which can look like this, this, or this. It's not always going to be a min or a max, but it could be a min or a max. And so we have to include him in our critical number list. And then after you draw your number line, you use your first derivative test. That will tell you whether you are looking at a min, a max, or neither. If you're decreasing to the left of that guy and decreasing to the right of that guy, then you have something like this. If you're decreasing to the left of that guy and increasing to the right of that guy, that means you would have a local min. If you are increasing to the left of that guy and decreasing to the right of that guy, that means you would have a local max. So if our goal here was to sketch a graph or find the mins and maxes, my next step would be to draw a number line for f primed or h primed. Other questions on this one? Okay, so let's see, we've got study guide 235, and I think that was 10, right? No, that was 5. Okay, so 10 is next. Yeah, this is good. Sketch x plus sine x. My domain here is all real numbers because there are no restrictions from sine or from the x itself, polynomial, and then this trig function has domain all real numbers. I don't have any asymptotes. No VA, no vertical asymptotes, and no horizontal asymptotes. I can look for symmetry. And this is a nice example because here we do have some symmetry. If I look at f of negative x, that's negative x plus the sine of negative x, which is negative x. And then sine is an odd function, so this negative will pop out. Which is negative x minus sine of x. And then you can factor your negative and you get negative x plus sine x. So this is negative f of x. So when we check for even and odd, when we check for these symmetries, that always means we're going to look at f of negative x and see if we can simplify it either to negative f of x or plain old f of x. Here, f of negative x simplifies to negative f of x, so f is an odd function. Hence, the graph has origin symmetry. Intercepts. Find my y-intercept first. This always comes from plugging in x equals 0. So here, f of 0 is 0 plus the sine of 0, which is 0 plus 0, which is 0. So the point 0, 0 is on the graph. X-intercepts here are actually very hard to find. If you try to solve for x-intercepts, you're going to have a bad time. In general, to find x-intercepts, you need to solve f of x equals 0. So you would be trying to solve 0 equals x plus sine x, which is the same as saying sine x equals negative x. One solution to that equation is x equals 0. But then it's hard to tell whether or not there might be other solutions to this. Certainly if x is bigger than 1, then there are no solutions because the sine function only ever outputs things between -1 and 1. So we're going to put a pin in this for now because this is actually really, really hard to solve. And I don't mean hard to solve like you guys don't know how to do it. I mean, even the most talented mathematician in the world would look at this and say, ooh, I don't know what to do. So besides x equals 0, not sure. Okay, that's it. We've looked at our domain, our asymptotes, our end behavior, symmetry, intercepts. So now we would jump to our number line work. I'll look at f primed. Here that's 1 plus the derivative of sine of x is cos x. And this is never undefined, but if I set it equal to 0, that's the same as saying -1 is equal to cos x. And that happens infinitely many times. Where is cos x equal to -1? Well, that's any time you run through the bottom, the far left side of the unit circle. So this has solutions x equals pi, 3 pi, 5 pi, and so on. Anytime you hit the far side of the unit circle over there, right? Over here is where cos x is equal to -1. So that's any odd multiple of pi. Maybe I'll graph this thing from 0 to 4 pi and see if we can't get a feel using the symmetry. Or even just 0 to 2 pi. Let's go 0 to 4 pi, why not? So my number line for f primed will have pi. And I'll put 3 pi on here. I don't think the problem specified where they wanted us to sketch. Yeah, they don't. But because I've got an infinite list of solutions here, I can't actually put all of them on the number line. So we'll look at the interval 0 to 4 pi. So I'm going to forget about this guy for now. I'm just going to look at the interval 0 to 4 pi and then try to get a feel for what it looks like there. If I test something to the left of pi, like pi over 2, the cosine of pi over 2 is 0. So So here I'll test x equals pi over 2. F primed of pi over 2 is 1 plus cos pi over 2, which is 1, because the cos of pi over 2 is 0. In particular, it's positive. Between pi and 3 pi, I could test 2 pi. F primed of 2 pi is 1 plus the cos of 2 pi. The cos of 2 pi is 1, so this is 2. So we're positive here also. And over here, I said I'm only going to go out to 4 pi. So between 3 pi and 4 pi, I could test, I don't know, 3 pi plus pi over 2. What is that? Oh, my next interesting guy is 5 pi. So let me go ahead and test 4 pi. So f primed of 4 pi, that's 1 plus cos 4 pi. And the cos of 4 pi is also 1. So what you see is that f primed is actually never negative. It's positive, and then 0 here. Positive, and then 0 here. And this pattern we can expect to repeat because this function is a periodic function. So I would add a little note here. F primed is periodic with period 2 pi. F itself is not periodic because of the x here. But f primed is just this shifted cosine wave. So he is periodic. In any case, here's my number line for f primed. So I'm going to go ahead and take f double primed, start working with him. Let's do this. All right. So f prime primed of x is the derivative of f primed. The 1 will differentiate to 0. The cosine will differentiate to negative sine. So f prime primed of x is never undefined, and it's equal to 0 when sine x equals 0. And we know the solutions to this. These are 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, etc. All right, sine x is equal to 0 at any integer multiple of pi. Again, I said I'm going to focus on the interval 0 to 4 pi for the purposes of this problem. So I'll just plot the ones that are between those. So I'll take 0, pi, 2 pi, 3 pi, and 4 pi. And this will be my number line for f double primed. If I look between 0 and pi, sine of x is positive between 0 and pi because I'm on the upper half of the unit circle. So f double primed, I don't even need to test points here because I know this function really well. Sine of x is positive between 0 and pi, so negative sine of x is negative between 0 and pi. Between pi and 2 pi, sine of x is negative because I'm down here at the bottom. So the negative sine of x, f double primed, will be positive. Between 2 pi and 3 pi, I'm back up on the top part of the unit circle where sine is positive. So f double primed, negative sine of x, will be negative. Between 3 pi and 4 pi, again, I'm down here where sine is negative, so negative sine x which is f double prime, will be positive. So what I don't have is the information for f itself. It's kind of hard for me to figure out where f itself is positive and where f itself is negative. But if you think carefully, you can string together the information here and the information from the very start. Here, looking at the x-intercept stuff. So I know that I go through the point 0, 0. And I know that f prime is always positive, which means f is always increasing. If you go through the origin and you're always going uphill, that means you're positive everywhere to the right of 0 and negative everywhere to the left of 0. So there are no other x-intercepts. 0, 0 is the only one. So my summary of number line work looks like this. I'm going to focus my attention just to the interval 0 to 4 pi. So 2 pi is right in the middle, pi is here, 3 pi is here. Between 0 and pi, f prime is positive and f double prime is negative. And also I know f itself is positive. So f is positive, f prime is positive, f prime prime is negative, which means we are here, f of x is positive, increasing, and concave down. That's between 0 and pi. Between pi and 2 pi, f primed is positive, f is positive, f primed is positive, and f double primed between pi and 2 pi is also positive. So f of x is positive, increasing, and concave up. And we continue like this. Between 2 pi and 3 pi, f is positive, f primed is positive, and f double prime goes back to being negative. So f of x is positive, increasing, and back to concave down. Between 3 pi and 4 pi, f is positive, f primed is positive, and f double primed goes back to being positive. So f of x is positive, increasing, and back to concave up. So the question then is, well, what's going on? I don't have any local mins or local maxes because f primed is always positive. F prime never goes from positive to negative, meaning my function never goes from increasing to decreasing, which means I could have never gone through a max or a min, because to do that, you have to go from being increasing to decreasing, and my function is always increasing. So no mins or maxes. But I do have a bunch of inflection points. At every single one of these, I go from concave down to concave up, or concave up to concave down to concave up. So I have inflection points at x equals pi, 2 pi, and 3 pi. So I should find the points, should find the actual points. The first one I have here is at pi comma f of pi. So that's pi comma, if I plug pi into the original, I get pi plus the sine of pi. The sine of pi is 0. So this is just pi comma pi, because f of pi is pi plus 0. I have another inflection point at 2 pi comma f of 2 pi. So to find that y value, again, I would plug 2 pi in here. That's 2 pi plus the sine of 2 pi. But again, the sine of 2 pi is 0. So this is 2 pi comma 2 pi. And then we have another IP at 3 pi comma f of 3 pi. And f of 3 pi, again, if you plug 3 pi in here, you just get 3 pi. Okay, so I have these 3 inflection points. No mins, no maxes. My x-intercept is the same as my y-intercept, is 0, 0. So if I want to draw the graph, I start by plotting this info, and then I try to connect it with the appropriate shaped pieces. I'll mark this as pi, 2 pi, 3 pi, 4 pi. I know that I have an x-intercept here at 0, 0. I know that I have an IP at the point pi comma pi. And I'll mark these same units off here. So I know that this is an IP. I know that 3 pi comma 3 pi is an IP. 2 pi comma 2 pi, sorry, 3 pi comma 3 pi. And 4 pi comma 4 pi we haven't talked about, but we would hit the same thing there. So then what's going on between 0 and pi? F is positive, increasing, and concave down. So we start off doing something like this, increasing, concave down. And then increasing, concave up. And then increasing, concave down. And we continue like this. We're never decreasing. And if you pay careful attention to my f primed number line, let's come back here, at pi and at 3 pi, I should have horizontal tangents. My concavity changes there, and I have a horizontal tangent. But at 2 pi, I don't have a horizontal tangent because f primed is not 0 there. So this is an inflection point and a horizontal tangent line. Inflection point and horizontal tangent line. And then using symmetry, remember this is an odd function, I could say by symmetry it has to continue like this over here. Something like this. And that's a pretty good graph. This IP and horizontal tangent line is at the point pi comma pi. This IP that is not a horizontal tangent line is at 2 pi comma 2 pi. This IP and horizontal tangent line is at 3 pi comma 3 pi. And that's a pretty good graph. If you compare this to the options you had to choose from, shouldn't be too hard to spot. This guy doesn't have the right y-intercept. This guy has the correct y-intercept and appears to have the correct shape. So we have to try and distinguish between, let's see, this guy doesn't have the right y-intercept. So it's either this one or this one. Okay, is it the top left or, sorry, top right or bottom right, and why? I claim it's the top right. Because if you look at the origin here, I don't have a horizontal tangent line. But the bottom right guy does have a horizontal tangent line at the origin. F primed of 0 is not 0. F primed of 0 is 2. This guy has the correct slope at the origin. So this is a horizontally shifted version of my guy. My guy is this guy. So you draw your graph, and then you compare to these graphs. Both of these guys on the right have the right shape and the right y-intercept, but only of them has the right behavior at the origin. All right, my guy does not have a horizontal tangent line there. This guy does, so it has to be this guy. Cool stuff, right? Okay. So 2, 3, 5, 10 from the study guide. Let's go back to the homework. I see 8 and 16. Number lines.
Professor,
Yes.
can you show the work so I can take a screenshot of it?
Sure. So I'll close that because we're going back to homeworks now. Okay, so here, if you're taking screenshots, here's page 1.
Got it.
We find our domain, and there is our F primed work and our F prime number line. And then here is our F double primed work and our summary number line.
Got it.
Something we might want to add is that even though we don't have mins or maxes, we do have horizontal tangent lines somewhere. Those horizontal tangent lines came from places where F primed was equal to 0. And those were at pi and 3 pi. So you do have an HTL here, and you do have an HTL here. Even though there's no min and no max, that's useful information.
Okay, I got it.
Sweet, and then here's our graph.
I have another question.
Yeah.
How long should we be spending time on these problems? Like, how long should we, like, on average? Because they're all pretty, like, they take a long time to do.
If you're working through the homework, like these 4.5 curve sketching problems, totally appropriate to spend any 20 minutes to an hour on one of them is fine. The problems that I'll give you on the test will be fairly quick, right? So I might give you a problem like this, but with a polynomial or something that's easy to do all of the algebra.
Okay, because that was my question, because I know that there's gonna be like probably like around 15 or 12 questions on the exam, and if like one of the problems takes over like 40 minutes for you to show us how to do it, then it's kind of concerning.
I understand. Yeah, that would be savage. No, so my purpose on this test is not going to be to give you a bunch of problems that take forever and ever. So if I give you something like this, where I ask you to do all of these things at once and draw me a graph, I promise you that that problem will be relatively straightforward. Either a very simple rational function, simple trig function, or polynomial function, something like that.
Okay, sweet.
All right, so let's move on. I think there were some homework questions requested. Homework 9, number 15, homework 8, number 16. Let me go back to homework 8 and look at number 16. Oh, wrong class. Homework 8 for you guys, number 16. So we want to find critical numbers for this guy.
Question, sir, can I take the picture of the graph?
Yes.
Okay. Thank you.
Welcome. So homework 8, number 16 asks us to find critical numbers for this guy. So let me write him down. All right. Sine and cosine both have domains, all real numbers. So any place where f primed is 0 or undefined will automatically be a critical number. We don't have to worry about domain stuff. So I'm just going to take f primed. That's going to be negative 12 sine theta, because the derivative of cosine is negative sine, plus 6 times, and then here I need the chain rule. Sine squared theta differentiates to 2 sine theta times cos theta, like so, which is the same as negative 12 cos theta plus 12 sine theta cos theta. So I want to find places where this guy is equal to 0. Sine and cosine are never undefined, so I don't expect that this will ever be undefined. So I'm going to factor 12 cos theta out. And what's left is negative 1 plus sine theta. Now that I have this in factored form, I can set each factor equal to 0. 12 cos theta equals 0 if and only if cos theta itself is 0. And cos theta is equal to 0 at the top and bottom of my unit circle. So there's infinitely many solutions because cosine is periodic, and they each come from one of these families. I can think of it as coming from the pi over 2 family, coming from the top point, or from the 3 pi over 2 family, coming from the bottom point. And remember the way this works from your trig class, you have to add integer multiples of the period of this function to your 2 fundamental solutions. So you get your 2 fundamental solutions to any trig equation from the unit circle, and then you extend using the period of the function in question. So the period of cos theta is 2 pi, so I have to add any multiple of 2 pi, and the way we write that is as plus 2 pi k, or plus 2k pi. You can shuffle the k wherever you want, but you add multiples of the period. So all of those, there's infinitely many critical numbers for this function. 2 infinite families just come from this stuff. And then I'll have another infinite family or 2 from this guy. If I set this equal to 0, that's the same as saying sine theta equals 1, which actually only has the 1 unit circle solution. That's on the right-hand side. Oh no, sine theta equals 1. That's at the top here. Oh, so there's overlap. Nice. Yeah, that's neat.
So I think you have the derivative of 12 cos as negative 12 sine,
Yes.
and then somehow it changed to negative 12 cos.
Oh shit. I'm sorry.
But
Yeah, you're right. Angelica, you're saving the day today.
you're welcome. I
Negative
got
12 sine. Okay, yeah, this should be sine. Sorry, yeah, I just copied this down wrong. Negative 12 sine theta. Okay, so instead of factoring 12 cos theta out, I'm going to factor 12 sine theta out. That was looking too easy. So when I factor 12 sine theta out, this piece will become a negative 1, and this piece will become cos. Okay, so set this equal to 0. That's the same as saying sine theta equals 0. I look on my unit circle, that's over here and over here. So same sort of thing, theta is either 0 plus 2k pi, that's this first guy, or theta is equal to pi plus 2k pi. And then from this guy, I'll have negative 1 plus cos theta equals 0, which is the same as saying cos theta equals 1. So I look on my unit circle for where cosine is equal to 1. That's this guy. So actually we have overlap either way, but definitely different solutions. So this is going to be theta equals 0 plus 2k pi. So altogether, these are my critical numbers. These guys together with these guys. And of course, there's overlap. The first set of solutions here are the same. So our critical numbers are theta equals 0 plus 2k pi, which is just 2k pi, and theta equals pi plus 2k pi, where k is any integer. If they asked us just for the critical numbers between 0 and 2 pi or something like that, then I would just take the 0 and the pi, right? Those would come from plugging in k equals 0. But if you want all of them, these are all of them. And I think they asked for all of them, right? Yeah, and you let n denote arbitrary integers. So instead of a k here, they want you to use an n. Well, that's it. That's your guy. So that was 16 from homework 8. If we move along, Carson asked to do number 6. Do you mean in the study guide or in the homework? Carson?
The study guide.
Okay. I'm going to come to homework 9 next because that was asked for earlier. So homework 9, number 15. Here we wanted to find intervals of increase, decrease, all that good stuff. I think this will probably be the last one we have time to do. So if we wanted to see any extra problems, I would come by office hours this afternoon. I will have my normal office hour. Okay. So to save time, I just write find all the good stuff for f of x equals x squared minus x minus ln x. So by good stuff, I mean intervals of increase, decrease, local mins, local maxes, intervals of concave up, concave down, and inflection points. F primed is where I get started. The derivative of x squared is 2x. The derivative of x is 1. And the derivative of ln x is 1 over x. If I want to find where this is 0 or undefined, I need to have a common denominator. And the only denominator I can use here is x. So I multiply this by x over x. I multiply this by x over x. And this piece already is 1 over x, so he doesn't need any work. So I find that f primed can be written as 2x squared minus x minus 1 over x. And we should note that the domain for this function is the open interval from 0 to infinity. That's coming from the natural log. You can only plug strictly positive numbers into the natural log. If I want to find where f primed is 0, I set the top to 0. If I want to find where f primed is undefined, I set the bottom to 0. Let me take care of that first. So f primed is undefined when the bottom equals 0. That means x equals 0, but 0 is not in the domain of the original. So I don't need to worry about him. F prime is equal to 0 if the top is equal to 0. And that means 2x squared minus x minus 1 is equal to 0. So I should try to factor that. This means I need two numbers that multiply to -2 and add up to -1. So that would be -2 and 1. So this is 2x squared minus 2x plus x minus 1 equals 0. You can factor a 2x from the first bit and you get x minus 1. You can factor a 1 from the second bit, you get x minus 1. So you get 2x plus 1 times x minus 1 equals 0. So f primed is equal to 0 when x is equal to 1, or from this guy, -1/2. But again, just like I don't need the x equals 0 guy because he's not in my domain, the -1/2 guy is also not in my domain. So I rule him out. So the only critical number is 1. That's the only place where f primed is 0 or undefined, which is in the domain of the original. So my number line for my number line for f primed just has 1 on it. To the right of 1, I could test 2. If I plug 2 into f primed, the denominator will be 2, and the top, so here I'll test x equals 2. F primed of 2 is 2 times 4 minus 2 minus 1 all over 2, which is 8 minus 2 minus 1 over 2, which is 5 over 2, which is positive. And because the factor here is a multiplicity 1 factor, the factor that gave me that 1, I know I will change sign as I jump over it. Or you could test 1/2. Can't test 0 over here because 0 is not in the domain of the original, not a part of this thing. Also, 0 makes f primed undefined. So you'd have to test something between 0 and 1. But much faster to use the multiplicity trick. So f is increasing. On the interval from 1 to infinity, and f of x is decreasing on the interval. Think about your domain, 0 to 1. Not from -infinity to 1, because my function doesn't even start playing until 0. He doesn't exist to the left of 0. So you can think of 0 as being like a hard cutoff over here. To find concave up, concave down, I need to take the second derivative. I think the easiest form to do that in would be here. So I'll rewrite f primed. It's 2x minus 1 minus x to the -1. So f double primed is the derivative of that. The derivative of 2x is 2. The derivative of -1 is 0. And the derivative of x to the -1 is -x to the -2. So this will become minus -x to the -2, which is the same as 2 plus 1 over x squared. Again, I need a common denominator. I multiply the 2 by x squared over x squared, and I get 2x squared minus 1 over x squared. Sorry, plus 1. Plus 1 over x squared. As far as I can tell, this is never going to be 0 or undefined. So f double primed is undefined when x equals 0, but again, not in the domain of the original. So I don't worry about him. And this top is never going to be 0. Because 2x squared is always positive. So this has no real solutions. You can subtract 1 from both sides, divide both sides by 2, but this has no real solutions. So in other words, the concavity of f never changes. The number line for f double primed, has no numbers on it. You can test whatever you want. Again, 0 is a hard cutoff on the left because the domain of my function is 0 to infinity. You could test x equals 1 if you want. But f double primed is always positive. So f prime primed of 1 is 2 plus 1 over 1 is 3. So we're always concave up. So no inflection points. I'll finish this here. So f prime primed of x is always positive. Therefore, f of x is concave up on the interval 0 to infinity, its whole domain, and concave down nowhere, or DNE. And as a consequence, we have no inflection points. There's no place where you go from being concave up to concave down, or from concave down to concave up. And that's it. We're increasing from 1 to infinity, decreasing from 0 to 1. So we do have a min. Let's see. So we go from decreasing to increasing at 1. So I do have a local min. This tells me I have a local min at x equals 1. And to finish things up there, you would want to say what the min value is. So you'd have to say what f of 1 is. F of 1, I'm pretty sure, is 0. Yeah, 1 squared minus 1. So the point here is 1 comma 0. 1 squared minus 1 minus the natural log of 1. So this is all of our stuff. Got a local min there. No inflection points. We're concave up everywhere on our domain and concave down nowhere. And our intervals of increase and decrease are these. That's everything. Questions on the work here? This is f primed. So these problems do involve quite a bit. I would expect on your exam for there to be one problem where I make you go through all this sort of stuff, finding all the different shapes of the graph on the different intervals and then drawing the graph. One like 4.5 problem. And then probably a few separate problems where I ask you to do different things on their own, like identify any local mins, local maxes, absolute mins, and absolute maxes for a specified function on a specified interval. Expect some related rates stuff and some chain rule stuff on its own, because we haven't really tested that. And that's going to be the majority of the test, right? There's not a whole lot of time for other stuff. The true, false, and multiple choice questions, make sure you know your theorems, right? The mean value theorem and Rolle's theorem are a good source of true, false, multiple choice questions. The first and second derivative tests are great sources of multiple choice and true, false questions. So look through the review for chapters 3 and 4 and take a look at those true, false questions. Those will get you ready for the true, false on our test. And then make sure that you're comfortable doing all this number line work, because this is really where everything else comes from besides related rates. So practice related rates, this number line work, and the true false problems from the review in the textbook once you finish the study guide, and you'll be in pretty good shape. I do have to get moving now because I've got another class that starts in a little bit. So are there any last minute questions here? Any questions on this problem?
Yeah, to join you through office hours, so how this work? So I never did it. So.
Just go to the main page for Canvas. Here, I'll show you. Come to our class in Canvas, go to the home page, and you'll see right here, office hours, and there's a Zoom link. Click this link, and you'll join the office hours.
Okay, thank you.
Oh. Anything else before we get going? Okay, so Carson wanted to see one more problem. Unfortunately, I don't have time to do that, so I'll ask you to bring that to office hours this afternoon if you can, Carson. If you can't bring it to office hours, send me an email. Let me know what homework or study guide that's coming from, and I can send you a solution, or if you can come to office hours, that would certainly be easier. Otherwise?
Yeah, I'll get with you in the office hours. Thank you.
Cool, okay. Otherwise, then I won't be seeing you guys Friday because you have the exam during class time. Remember how that goes. I can post another announcement reminding you the exact protocols for the exam, but it would just be a copy paste of the announcement from exam 1. It's going to go the exact same way. If you anticipate any problems, if you don't have a webcam or you haven't been able to get HonorLock to work, you need to reach out to me today. Today is like the last day I can try to solve those problems for you. And then after this, we'll be locked in. Remember, as you're writing the solutions to the exam, please put one problem per page. Some folks put multiple problems per page last time, and it was okay. Some folks put multiple problems per page last time, and it was a nightmare hellscape for me trying to figure out what went with what. Organization is so friggin' important, right? Especially here. I'm pretty organized with my work, but even me looking at this, it's a little sloppy, right? It's a little bit messy. There's just so much to do that it kind of gets all over the place. One problem per page, number your problems, right? Put the problem number at the start, and please put your name on the page. Those sort of things make my life when I grade a lot easier. I know everybody wants their grades fast, so the more you can do to keep your shit organized and easy to read, the faster I'll be able to get the grades back to you, and I know we all want that. So that is it, all right? I'll either see you in office hours this afternoon or next Monday after the test. I wish you all the best of luck. If you have questions, please come to office hours, send me emails, Canvas messages, talk to each other. Do whatever you can to get as much practice in as you can. And that is it, okay? I hope you guys have a lovely rest of your day, and I'll see you either later today or Monday.